Hosting provided by Host Tornado. They offer website hosting packages, dedicated servers, and VPS solutions. Host.t.net. Programming Throwdown, episode 38, SimD. Take it away, Patrick.
We're going to start off here, episode 38, with a question from a viewer. Oh, well, we don't have viewers. A listener question.
We have
Although
viewers.
Today we do have viewers.
This is actually the first time we have viewers. Last time we had viewer.
But I don't know that it was one of our viewers who asked this question. It was definitely a
good
listener,
point.
though.
That's a good point.
A listener. And they asked, well, I should give credit to at least the first name of the person, but I don't have it. But it's okay. You'll know
I'll
who
look it
you
up.
are. And the question was, do computers ever make mistakes? And this is a good question. And some people, I think this is actually posted in our Google Plus community. And so actually someone had written back, and we'll share our own opinions. But one of the things when you first are introduced to computers is you're told, like, the computer doesn't ever make a mistake. It only does what you tell it to do. And sometimes as programmers, we write bugs or faults.
So quick interrupt.
Yep.
The asker was Matthew. I won't say his last name. Actually, his last name is right on G+. It was Matthew Alabastro. Thank you for the awesome question. We love it.
Yep, thank you. And so you're always told computers don't make mistakes, but that it's always a programmer's fault or some software that was broken or wrong.
Mm-hmm.
And then the person who responded actually got the same thing that first came to my mind when I read the question, which is that there actually is sometimes the processors, the thing which are simply the brain of the computer, but the thing that we think about when we think about a computer, you're typically thinking about the processor doing the work, and it does sometimes have logic flaws. Things that it's supposed to do. And there's several famous ones, but one is that, sometimes you have different lines that are supposed to correspond. Like if you do a divide by 0, then that should be a certain kind of error. But sometimes that'll be actually triggerable by other stuff, or won't get triggered at all. And then this can cause a problem because it means your processor doesn't do the expected behavior. And we talked about one, I think it was last episode or 2 episodes ago, where it turns out the estimation for pi in some of the Intel processors isn't as accurate by several, like 10 bits or something, as it could be. And it leads to kind of errors in trigonometric functions near pi.
Yeah, I mean, another one, I'm just, there's a link to it. I'll put a link in the show notes, but there's this FDiv bug in like the 90s with Pentium where like they would... I don't remember this. I mean, I could read the article, but basically it's something to do with like the division, like calculating the remainder of the division or something. But yeah, basically they got it wrong in the processor. And, it just means that like there are certain divisions that, you can do them, but it won't give you the answer that you want it to. And, sometimes through some Christmas miracle, you can solve it in software by changing the firmware of the processor and things like that. But I mean, really, many times it's just there's nothing that you can do about it. I mean, it's etched. It's as if like you bought the wrong screwdriver or something, right? You're just kind of done. So,
but surprisingly,
go ahead.
sometimes these bugs, quote unquote bugs, linger around. So like there's some quirk that wasn't intended, but then if you if Intel has like a quirk in their current line of processors, AMD is faced with the situation of trying to either replicate the bug or, fixing it, but then having, compiler writers trying to determine which processor is being used if they want to work around it, which is why it makes it difficult to fix it in software.
Yep. And I mean, a lot of this, there's one thing I didn't realize until I moved to the West Coast. There's a ton of cross-pollination. So, there's a ton of like Intel people who are at AMD and, AMD people at Google and Google people at Facebook and Facebook, you know what I mean? And so, obviously you can't just take the technology from one company and give it to the other, but it's like, if at the end of the day, there's like a core group of people and they agree on a way to do floating point, and then one of them leaves and goes to AMD and he implements almost the exact same way, and now you have the same bug on 99% of the world's processors. I actually thought of this like in a totally different way, which is the not the common way, obviously, because no one else seemed to think of it this way. But also, it's like it's very esoteric in hindsight. But the first thing I thought when I saw this was, in the context of like machine learning and things like that, like do computers ever make mistakes? Like in the sense that do they not do what you want them to do? And I think that like this is actually like kind of interesting. It's really it's like now we're things are getting kind of very high level with computers, and I mean you're doing a lot of like statistical analysis and a lot of these like stochastic processes and things like that, and it's not really clear. Like at some point the computer will start making mistakes. Like right now it's like if anything is wrong, it's always our fault. And in reality, is like there's always, you as a programmer can change things, and the computer ultimately is supposed to be like reproducible, right? But like we're getting more and more into like crazy AI things, robotics, things like that. And so at some point, I mean, the computer will be kind of making mistakes. I mean, that's like, I don't know if that crossover will ever happen. It's kind of weird.
I mean, computers can make mistakes in certain ways, depending on how you think about it. Besides just we say, like, if you get sometimes my credit card, I've had a couple times, it detect what it thought was fraud, right? Which is some computer, there's no person saying they're looking at my credit card history. But some computer determines that my current spending habit looks a lot like someone who stole my credit card. And sometimes they're right. One time they were right.
You've been buying those like rugs, the Indian rugs or something? Yeah, that's like the number one thing. If someone steals your credit card, they will buy Indian rugs. In fact, somebody, when they had the whole PlayStation fiasco, my credit card was one of the ones stolen. And sure enough, Capital One calls me up and says, "Did you buy, 4 Indian rugs?" That was like the first thing they asked me.
That's really odd. Well, the one I've always heard before.
I think they're very expensive.
Yeah. Oh, maybe. Is that teenagers typically go buy shoes and then buy gas for them and all their friends. So if you fill up like me and my spouse's car, and then I went to the mall and bought something or whatever, and like that'll trigger it.
Oh, wow.
But no, specifically what it triggered mine was I made a change in I had moved, so I made a change in my address, and then I ordered some computer parts online, and apparently that also looks exactly like someone stole your credit card, which makes sense. But some computer made a mistake, right? Like I didn't commit fraud.
Yeah, right.
But did it really make a mistake? No, it probably did execute the rules it was told to. But from my point of view, it was a mistake. There was no fraud.
Yeah. I mean, that's the kind of thing. Like if you, I'm assuming they built this really complicated fraud system that like projected all of your credit card purchases to some like really high dimensional latent space. I mean, at some point, it's like, I guess like making a mistake comes down to responsibility. Like, I mean, I guess at the end of the day, you're always responsible for the computer, But I mean, like, look at like these algorithmic trading computers, where like they do machine learning to like predict stock market prices and things like that. I mean, in that case, like you're saying, look, the computer's doing the trading. Hopefully it wins more than it loses. But at the end of the day, it's like I don't know if that's really, the responsibility thing is kind of fuzzy.
So another mistake can be. It has sort of gotten to your stochastic processes thing, but that if you are running your processor at high temperature or close to its power limits, you can have glitches, which cause problems. Or you always hear this classic thing, but it is actually true that there are cosmic events, radiation, cosmic rays, which cause logic levels to flip or invert temporarily, and can inject noise at some level into the computer. And then the computer can think a 0 is a 1, right? And then all of a sudden that changes everything.
Yeah,
now your very large number is now a large negative number because the first bit got flipped, right? Like that can happen. Statistically it's, basically not going to happen, but for someone it will happen.
Yeah, there's this interesting TED Talk. It was from the security chief of Twitter. And basically, she said, like, I don't remember exactly. I'm going to kind of butcher this, but she's saying something like, if there's a 1 in a million chance that some crazy, event would happen, like your stalker happens to find you on Twitter randomly. Like, if that's a 1 in a million chance, then it happens 50 times an hour in Twitter. You know what I mean? Like just and it's just kind of like
No, I guess that's what I was trying to say. Yeah. So the chance
Yeah.
of your computer having a cosmic event change it in a meaningful way is, 1 in a billion. But the chance of a cosmic ray affecting someone's computer in a meaningful way is, very high in a given day.
Yeah, right.
So, but yeah, okay. I don't know.
Yeah,
Does it make
cool.
any relevant difference today? Probably not. But it is an interesting question.
Yeah, totally. So for like kind of, do you want to do news first, or do you want to cover this?
Let's
Intro
cover this.
topic.
Let's cover this.
Okay, cool. So yeah, I don't know how I got on this, but somehow So I feel very compelled to, like, I'm working with a lot of people who are just fresh out of college, and so it's kind of cool. Like, it feels like you're looking at yourself, like, but younger, or just like less experienced, because like they're doing all the same things I did, and it's like I can't obviously fault them for it, but it's like I think it's like in hindsight it's clear, like there's like lessons that neither one of us, like no one, myself nor any of these other people, have learned the easy way, and we're all having to learn it the hard way. Actually, well, hopefully I can make it so that they don't have to learn it the hard way. But I wanted to take a little bit of time to talk about like rookie software engineer mistakes.
But
And
so the TLDR of this intro is that you're getting old. I mean wise. Wise.
Womp,
You're
womp.
getting wise.
Oh, there was a Quora question, and it said, what do old software engineers in Silicon Valley do? Or like what happens to old software engineers? And the number one answer was this guy. He said they become well-paid software engineers. I don't know if that's true or not, but it was
Okay.
kind of interesting. It made me think that like there really aren't that many old software engineers. Like you don't see a lot of like 50, 60-year-old software engineers, and there's probably a bunch of reasons for that.
Wait,
Um,
okay.
anyways, I digress.
Yeah.
But so that's why we're thinking we're old, right? Anyways, so a couple of rookie software engineer mistakes. One of them, and this is a big one, is like making assumptions, and it's either because you want to kind of save time or save processing, or you don't want to change the schema or something like that. So like I purposely didn't like, no one on my team actually said any of these or anything like that. But this is like a fictitious example is, you have some document system, and you store the timestamp for all the documents, and then all of a sudden you need to know whether a document was created by an admin or not. And rather than having some Boolean which says created by admin, you say, oh, I know what I'll do. If the timestamp is negative, I'll just flip the sign of the timestamp. If it's negative, then it's an admin. And so like things like that work, but the problem is you're kind of setting up a landmine for your future self. You know what I mean? Because you're now like adding this cognitive overhead where you have to remember this sort of association that you only made up because it was kind of convenient, given the circumstances. And so you see just a ton of this kind of stuff where, people will just kind of, it's not really a shortcut, because like often it doesn't
it's just
save that much
overloading.
time.
You're overloading. Yeah, I do see this a lot.
Yeah,
Optimization.
exactly.
Yeah, you're overloading a field or a value to mean multiple things, and it just makes it convoluted instead of breaking out to explicit fields.
Yeah, exactly. I mean, another case of this, it's like a little bit of a different vein, but it's where someone starts off with like current measurement, like double current measurement, and then they need the previous measurement. So they're like double previous measurement, double current measurement. And you're like, okay. But then they realize they need the last 10 measurements. And they're like previous measurement. You know what I mean? And it's just like, it just grows organically. And the next thing you know, you like have this ridiculous thing that could just be an array, right?
Or the other pet peeve of mine is even in, I guess this is more common maybe in dynamically typed languages like Python. But, and I even see people do this in C, but like you'll have some, unsigned 8-bit integer that is getting some value from a function. then later they also use it to get a value from a different function, like later in that function, you know. But now these are two different things, but they just reuse the same variable. And it's up here the variable meant this, now down here the variable means this. Like, why don't you just create a new, like the compiler will, you know, optimize this away. There's no reason for you to reuse the same variable name twice. Like in a loop, like if you're looping and the loops aren't related, like fine. Like I'm okay like having the variable I, counter or whatever be used. But like syntactically, like they don't. It's just like, here's one value, then here's a value from a completely unrelated function that also just happens to be of the same size. And I no longer needed the other one, so I'll just reuse the name. It's like, oh, just create a new name.
Yeah. That stuff is brutal. Another one that I see a lot is people who don't put like asserts or exceptions or like to some extent tests in their code. I mean, everyone always complains about no tests, but even just like asserts and exceptions, you know, I mean, it doesn't take much time to, as you're going through, say, okay, you know, I expect this list to have 3 things in it. So if it doesn't have 3 things, then blow up, you know? Like code, a lot of the code I write, like, you know, a few days later will blow up or a week later will blow up. And usually it's because some other part of the system like violated one of the assumptions that I wrote, you know? And, or even, you know, even if it blows up, like if it blows up like a year later, it's even better, right? Because instead of just some really weird runtime condition that maybe you don't even notice for a long time, it's like a year later, all of a sudden it's like, boom, exception. I expected the list to be 3, now it's 4. And usually, you know, the exception will fire immediately after someone makes the change that causes the problem, right? So you don't have these like really weird latent issues that you have to like go back and play detective to figure out, you know?
As you work in really, really large systems, this is where like continuous integration and unit tests become absolutely crucial. So you even if you test your code, if you've changed something that other people were assuming about your code, and they don't also have tests, or you know, there isn't some system kind of doing integration testing, then it can go undiscovered for a while.
Yep. Yeah, totally.
That's hard, right? So
somebody in the chat said they don't like it when -1 is used to represent a failure state. That is another good thing. Like you see that where it's like the function, you know, returns an int, but yet, you know, they really want to return an int and, you know, something else for the status. But instead of returning like a pair, they return an int and they're like, okay, this is going to be positive, except it's -1 if this, and it's -2 if like cows are flying, and it's -3 if it's a Monday, and you're just like, I can't deal.
Yeah. Well, similarly, yes, I did have this problem with a new person on a team. I had to help try to convince them, which I don't know how successful I was, but they had where they would call some computation function, it would return a result. Then you needed to call another function that said whether the value returned was currently valid or not.
Mm-hmm.
So like, you know, some state is being tracked and you need to call first and say, hey, is this other function going to be valid if I call it? Or if I've called it, is it currently valid? And I was like, why don't you just return Boolean of whether it's valid? And then like, you know, in this case it was C. So, you know, and then pass a pointer in, and then you'll know like if it's valid, the value in the pointer is now, you know, the pointer, the destination is now set to it. And they're like, I don't know. Like, why can't you just call this other function? And I'm like, well, because then if someone doesn't call that function, then like they have no idea if like you're just going to give them garbage.
Yeah, I mean, this way you're forcing them to
and they're like, well, they could ignore the fact that you're returning a Boolean. I'm like, yeah, but at least it's like more obvious to someone reviewing the code that, hey, why is this returning a Boolean and why are you ignoring it?
Yeah, right. So. I mean, in some languages you can't ignore return values, like not without the compiler getting mad at you and stuff.
Which is a good thing.
Yeah, that's right.
So, okay.
Cool, man. Do you do exceptions in C? No. I don't think. Yeah. So can't do anything there.
But I do have assertions.
Oh, okay, that's good.
And typically the way I see it is that you have assertions disabled when you're in release, but in debug you have them.
Yeah, that makes sense.
And so that always leads to this debate. Should you have non-disableable assertions? So then you end up with, debug only assertions and then regular assertions, and what is semantics around it. But it gets really
Yeah, then it depends sort of on, is your goal that the system survives anything?
yeah.
Or is your goal that like
is it
you fail
recoverable?
loudly?
Like, can you even theoretically recover from this?
Yeah, right.
So, yeah. Well,
The last one, reinventing the wheel. We there's like a ton of good, source code out there. A lot of it is very liberally licensed. You don't need to go and like create your own hash table and things like that. There's a lot of it for you. So yeah, I think this is a big one actually. And I think that like actually, connecting up libraries is really hard. I mean, especially in a lower level language like C, wiring together libraries, they might have different structs and you have to maybe do some fancy casting, or you have to, translate back and forth. And, doing that stuff efficiently is really hard. Like, it's cerebral. And, coding something from scratch is much more like mechanical. In a sense, it's like easier. But you're when you code from scratch, you're going to introduce all these errors that you're going to have to debug. Like, you're not going to write perfect code, and you're not going to write code that's as well tested as an open source library that's ubiquitous, right? So so this is just another one that I kind of tend to see a lot of. So people
depending on your company,
to,
using open source libraries may or may not get you into endless waiting with the lawyers.
Yeah, so it depends on the license. Like, I think some licenses are... Am I a lawyer? No.
Yeah, okay. Then if you work at any large company, regardless of that, this license is safe to use, they'll first want it to be reviewed by a lawyer.
Yeah, that's true. There are lawyer cats.
That's
yeah, I guess it depends on like usually the lawyer cats are pretty responsive. We had an issue where they didn't approve Emacs 24, but people were just using it. Nobody really thought anything of it. And finally somebody was like, oh, we should probably ask the lawyer cats. And they sent an email and it was approved like within a couple hours.
Yeah. Oh, I'm not saying all lawyers are bad. I just mean typically, depending on your company, they may or may as programmers, we sometimes say, oh, I know this license is, friendly or, fine to use, or this is in the public domain, I'll just go ahead and use it. But, there's also someone needs to be tracking everything you're using, because typically you're also supposed to at least give credit or cite that you're using something, right? So you have to make sure you have procedures in place so that you are keeping track of everything you're using.
Yeah, definitely. Actually, that's interesting. I wonder if there's like a Git hook for that, where it somehow, like, Git can become aware of what open source libraries you're using. I don't know. I don't know where I'm going with that.
Time for the news. So
you go first.
Okay, so I got the first article, and I'm not super good with Markov chains, so I don't know how good this description of Markov chains in this article is, but I thought it was a really interesting... this isn't how I traditionally see Markov chains, but it was an interesting approach that... the link will be in the show notes, but this person had read a Reddit posting of a programming challenge. How do you simulate this collection of particles undergoing radioactive decay, where you get, here's the starting number of particles in various states, and here's the probability that a particle decays from one state to another state, the second state to a third state, so on and so forth. And so they were talking about that, if you have 1 million particles, one way to do it is, essentially pick a random number for each of the particles, and then determine, based on the probability specified, if that particular particle, transitions state or not. And how that this, obviously is very costly and slow. And then instead how that, what they were saying was using Markov chains, but what amounts to creating a probability matrix, and what they were calling a transfer function, that you can essentially do a matrix multiplication and essentially do the same thing almost exactly. So you're not simulating each particle, but you're simulating kind of all of them simultaneously, undergoing this, and then what populations will you end up with at the end? It was a good article. So for really large numbers,
you're solving like the recurrence, right?
That's right.
Like you're solving like several steps in one.
Yeah.
Cool.
And so wouldn't I it didn't exactly, I know I'm trying to remember, but I don't think this would work for a really small number. Like if you had, 3 particles, right? Like it's random, so maybe it'll work, but you're going to have some weird stuff going on. But when you get into large numbers, right? Like it really all does, it all just becomes statistical.
Yeah.
So,
That was one of those things that like kind of blew my mind. I mean, a while back. It's like this idea where that sort of, I'm trying to see if I can grok this. So it's like, oh yeah, it's like, if you have a 50% chance of something happening, and everyone in America has that chance, then that means half the people in America have it and half don't. So this idea of going from like chance to, sample like populations, it's sort of like, yeah, like if 10% of the people have a tattoo, there's like 30 million people with tattoos or something like that. Like that whole going from like percentages to like, it's like, oh yeah, like at some point when the sample size is large enough, percentages become fractions.
Yeah,
like,
it's your it's not exact. Yeah. I'm not a statistician, but it's like your confidence interval, right? So like, if 10% have tattoos and you have 5 people, like how many people have tattoos? It's like, well, if all 5 did, that doesn't really prove anything. Like it doesn't say for certain that your 10% was wrong. It just like could be that you got really a very rare, a low probability event happened.
Right.
But if you're, like you said, 100 million people, and you say 10% have tattoos, you're going to be plus or minus a few, like, in the 99% confidence interval, your standard, like the amount of variance you expect to see is really low.
That's right. Yeah.
Yeah. So this is taking that same approach. But it was an interesting thing to remind us that when you start to deal with very large numbers of something, that you maybe need to step away from actually literally simulating it.
Yeah, actually this, I was given an interview question, which is exactly this problem.
Oh, really?
Yeah, the interview question was, I'm totally going to butcher this, but it was something to the effect of, it was something about like disk seeking. So, it's like you want to write data in a way where when you read the data, you could read it, just consecutively. And so it's like, but you don't know for sure how you're going to read the data. But anyway, it boiled down to like treating the problem of like going from one item of data you're reading to the next, treating it as a Markov chain.
Oh.
And it ended up being exactly this. So yeah. So read this article. You could answer an interview question. So mine is my news article is Axis: Destroy Your Friends with Math Functions. It looks pretty cool. I saw the video. I tried to play it, but they don't have a single player. So I haven't actually played it yet. But I think the idea is, there's some islands that are, you can think of them as like walls you can't hit. And then there's a tank or some enemy. And you have to draw some function that carves its way around these walls and hits the person. And it's like that game Scorched Earth.
Oh, yeah.
Yeah, where like you had the angle and the velocity of basically you defined a ray, and based on that ray you shot a projectile that arced with gravity and had to hit somebody. So it's that kind of idea, but they really took it to the next level. You come up with some crazy sine wave that like dodges a wall and hits somebody. So I thought it was pretty cool.
Sounds like a very
check
nerdy
it out. Yeah, I mean, if you want to destroy us, feel free to invite us. I don't actually know. I think the way the multiplayer works is you have to send someone a link or something. So,
all right.
But yeah, try it out.
They can play it in the chat room.
Yeah, let us know what you think.
Next article is why Python is slow. And for the sake of time, I won't go into all of the reasons enumerated in this article, but it's a very fascinating under the hood look at the mechanics of Python. So we talk about, Python is dynamically typed and interpreted, but what is the actual thing going on under the hood that causes it to be that much slower than C++ or whatever? And this guy did a really good job of breaking it down kind of piece by piece, and it gives a lot of insight that you would never think about kind of ordinarily. You might at a high level say, Python uses an object to represent an integer, but how exactly? And this article goes into that. So check it out.
Yeah, it's awesome. Yeah, so this next one is the day I lost a ton of money, and it's a
You're censoring yourself.
I'm censoring. Yeah, it's a ton of money. An S ton of money, and that's not like an S expression, different kind of S.
Oh.
But basically, it's from this guy who's like a day trader, and it just kind of blew my mind, like just like how this whole thing works, and how these people like, try like analyze the market or don't in this case, and just lose a ton of other people's money. I mean, it's kind of sad, but the whole thing is kind of interesting. It has some funny pictures and stuff like that. So
I haven't read this yet, but it is interesting. I was just skimming. I was like, whoa, what is going on here?
Yeah, so basically this guy, it's all about it's like your stereotypical, rise to power and then imminent destruction. So yeah, so
time for
on to
book of the
show. My book of the show is Emacs Quick Reference Card, but it's not only Emacs. In general, reference cards are pretty awesome. I have had the Emacs reference card like taped to my computer monitor for, I don't know, way too long. But
I have one of these for GDB.
Oh, do you really?
Yes.
Are there really that many commands in GDB?
Yes.
Oh, see,
have you used GDB before?
The only thing I've done with GDB is halt the program when there's a C++ exception. So I know like 2 commands in GDB.
Oh, there are, yes, many commands in GDB.
Okay. So yeah, in general, there's a reference card for almost everything. Like if you're doing Java, there's a Java reference card. And
I'm curious what a Java reference card has on it.
Yeah, actually, a good question. So the some of these things which are more like kind of muscle memory type things, it's really good to have a reference card. Sometimes like you're right there on the spot and you're like, oh, I want to, move this line up 2 lines, but like I don't want to like cut it and paste it, or like if you're feeling kind of adventurous, you can just look at the quick reference card, and it might have something. You can like slowly add it to your repository. So for things like Emacs, Vim, Eclipse, things which have keyboard shortcuts. Also, if you're learning a brand new language, rather than just like hitting Google every time, it's like, how do I do a for loop? How do I add? It's like have a quick reference card, and it will help you through. Like I had this when I was learning Swift. Someone had already made a Swift quick reference card, or maybe even Apple had made it. I don't know. I have to double check. But I had this quick reference card, and it reminded me of the obvious things until I got familiar.
Yeah.
So what's the Java quick reference card say?
Well, first of all, it's crazy like description of the collections. Like list is a part of a collection. An abstract set is related to a set, which is part of a collection. Like it has this like giant map on one part. And it has like all the keywords. So a lot of it is kind of, I don't know, maybe I consider too low level. Like here's the built-in types. Here's declaration modifiers.
Yeah, I think
but
are you looking at the one from NYU?
Like here's a declaration modifier, which I didn't know existed in Java. Strict FP. And it says strictly apply IEEE 754 to a class or method. But I don't know, like I can vaguely guess at what that means because I understand the words that are written here, but I don't, like I'd have to go look this up anyways.
Are you looking at the one from nyu.edu?
No.
Oh, I just typed in Java quick reference card.
I typed in just Java reference card. I'm looking at one from ac.uk, University of Glasgow.
Oh, okay. We're on the same one now. Oh, this is intense.
So I'm not sure that's useful.
The one from NYU, if you search for quick reference card, Java quick reference card, that one actually looks pretty good. It's the second link because the first one's an Android app.
Okay. Anyways.
But yeah, again, like this is really, I mean, this is for 2 things: either muscle memory kind of things, like Emacs, your editor, where there's like a huge, deep learning curve, and you just don't want to bite it all at once because a lot of it is situational, right? it's good for those things, and it's good for, you know, Java. I'm a Java programmer. It's day one, and you know, I don't know how to do anything yet. So, you know, if you're picking up a new language, you know, duct tape the quick reference card to your
duct
head.
tape. Oh, okay. We're just moving on.
Duct tape it to your monitor, and it helps a lot.
My book of the show, again, not being useful but being entertaining, is The Mote in God's Eye. This is a book co-written by Larry Niven and Jerry Purnell. It was written in 1974. So I really am digging these like 1970s and 80s books, because this one actually doesn't show its age as much as some of the other ones I've read. But I didn't realize it was written in 1974 when I was starting to read it. I was actually listening to this one on audio. But when I was starting to read it, I didn't actually realize it was written that long ago. And there were some weird mentions of like personal computers and like having audible, like almost like an audible modem was being described. And I'm like, oh, that's kind of weird. And then later I looked at, but I managed to read the whole story and not realize that it was written in 1974. And I looked it up and I'm like, oh, now that I know it's written in 1974, I understand these weird, like, the computers they did have were very limited, and they had weird nuances to them.
Yeah, right.
And so now I've ruined it if you decide to read it. But
it
is still a really good book.
In the future, we'll have microwaves.
Well, yeah. Well, so it's like, you know, oh, the magnetic memory storage was 1 megabyte in size. And it's like, what? Huh?
That's so good.
No, that's not exactly, but you know, something sort of like that. Basically.
Yeah, right. No, it's hilarious.
But they managed to do a really good job actually of avoiding specific technologies, which has got to be hard to do.
Yeah, definitely.
And so, but anyways, it's a story about. I don't like saying too much because I don't want to ruin anything, but it's a space sci-fi adventure. So.
Cool, man.
Check it out. I really enjoyed it, and apparently I just found out when I was getting the link for the show notes that there's actually a sequel that was written in like the 90s. So now I like want to read the sequel.
Oh, is it by the same person?
Well, it's two
That'd
people, Larry Niven and Jerry Purnell. They're both science fiction authors, and they got together to write this book and the sequel.
Wow, so they got together 20 years later to write the sequel?
So these people are like very prolific writers. So if you've ever heard of Ringworld, I think that was also, hang on, I'm gonna, which one it is, but that's Larry Niven as well in the 70s wrote this Ringworld book.
Oh, okay.
And I actually went to a talk that he did, and he's continuing to write books in the Ringworld series even as recently as a year or two ago.
Oh, wow.
So that's kind of crazy.
sweet.
Jerry Purnell also writes, still to now, I think.
Have you ever written a short story or a book or anything?
When I was in high school for school assignments.
Yeah, same here.
Okay.
I haven't ever written anything. I have a friend who is a English major, and she writes like short stories. They actually have, kind of like we have hackathons, they have like hackathons basically where it's like write a book in a month, and she just like writes 8 hours a day or something ridiculous.
All right, time for tool of the show.
Tool of the show. My tool of the show is OpenEMU, which is pretty freaking awesome. It's Mac only, which is a shame, but it has an unbelievable UI. So OpenEMU is what's called an emulator front end, and so what that means is they take a lot of emulators. Most emulators have like a command line interface, right? So you can just like execute the emulator. They might have a little GUI. If you run the emulator as like a little program, it'll pop up a little GUI, usually something just really crappy where you open a file, like ZSNES, right? Had that like really ghetto looking GUI. But if you were to like run ZSNES with arguments, you can actually like launch ZSNES and go straight to a game, right? So people have created front ends where the whole point is to like give you a better user interface, and give you like a window into your library of cartridges that you legally own. So this OpenEMU is pretty epic. So you can see from the screenshot if you're watching the Twitch stream, like it kind of looks like iTunes. Um, it has this like it actually downloads the cover art for you. So there must be some open source or some repository where they can get all these covers, because they have covers for almost everything, and downloads the cover art. It like analyzes the hash of the ROM to figure out like what game it is, and then it like corrects the file name, the title, all that stuff. So like it's like iTunes. It like legit like figures out the artist. In this case, the
I can't believe you just used
developers or
legit
whatever.
and emulation in the sentence together.
So this is pretty epic. Pretty exciting. They even have a cool website.
No.
And
no.
what?
Their website has my newest pet peeve is the equivalent of the blink tag, where you scroll down and stuff animates as you're scrolling. Like,
You don't like that?
oh, I hate that.
Really?
Oh, so
Oh,
much.
I think it's so good.
No.
Ah,
Why?
I think it looks awesome.
No, it's awful.
I think it's like
It's
it's
awful,
like
and
a
you
movie.
should feel bad if you write.
It's like a
websites
movie
that.
that you can watch
No.
over and over again.
No.
I'm watching
after
it.
the Apple announcement
watching
for
it.
like is it the new iPad or the new iPhone? They did a website like this, and it's just awful, so confusing. I very
What's
much
confusing?
dislike it.
There's one direction.
Well,
You
so this
scroll
one
down.
actually doesn't scroll back until you scroll off screen. That's even weirder.
That is weird. I like it when it's like I can sort
Can
of relive
rewind
the
it?
moment.
Ugh.
Yeah.
We had a website or news article like last time, and after I talked about it, I tried to like actually like read the whole thing, and I had to give up because it was like doing this.
I think it was Coin. Coin did this really badly, actually.
Okay. Well, it's my
when
new
we-
pet
when we were-
peeve.
Yeah. Okay. So I love your pet peeve. But anyways, so
Wait, no, you hate my
So-
pet peeve. No.
no, I love your pet peeve.
The
a
thing
peeve
I
that
hate,
you have
you
a
love.
pet peeve. That's not my pet peeve.
Okay.
Anyways, it's pretty cool. Another thing that these guys get right, which is genius, is like one of these obvious, like, can't believe I didn't think of that kind of things, is they bought one of the most common joysticks. Like if you just go on Logitech and try and buy a PC joystick, and also like the Xbox controller, and like they just bought all of these, and then for each one they configured it how it should be. And then if you plug in like a Logitech or Xbox controller, you don't have to like set all of the little keys, like say, oh, this is the up arrow on my controller, because they've done it for a lot of the
that's nice.
popular controllers. That's like, yeah, it's like a clever little add-on. It's pretty cool. Check it out if you're into that. So that's my Toolless show.
Mine is mint.com. I'm sure we've talked about it before, but I don't care. Because I was just thinking the other day how awesome it is.
Okay.
So if you've not used
My mint.com is completely broken. It's still I just haven't been keeping up to date. I need to like reconnect it to my accounts and everything.
So yeah, I think this is one of those things where it actually used to work better than it does now.
Oh, really? Wow.
Sort of, because I think, as far as I can tell, what happens is the credit card companies have their own solutions, right, and their own things they want to go, and so they're not super keen on the idea of like making sure to stay compatible with mint.com every change.
Oh, I
and
see.
so even though like as a customer I want them to stay compatible, they want to force me into using like American Express, use the your American Express app on your phone. It's like, well, I want to use Mint because I could just have one.
Yeah, right.
Anyways, so I do occasionally.
brutal.
There's periods where stuff stops working, and then they eventually fix it.
Oh, okay.
So I just bear through the pain. But when it works really beautiful, which is like I don't have to go to like my bank and my credit card and other stuff to like see. I just go to Mint, and it tells me like, here's where you're at, and they get the graphics right where I can like go and say how I've been doing over the last year, like what has my trajectory been? Have I been spending more than I make, making more than I spend? Like what are the months where I spend the most? Like why? All that kind of analysis, which for me, like I don't stick to a like fully allocated budget where it's like you have $10 to spend on coffee houses.
Yeah, that never makes sense. It's usually
Well, some
I think
people
what you're
do,
doing,
But I don't. But
Yeah.
what I do like is keeping tabs on where I'm spending money and like
right.
thinking about it. Like, hey, that's a lot of money. I should cut back on that because
Yeah, it's Amdahl's law, right? You get the biggest return for minimizing the biggest expense, right?
yeah, well, that and also just like the fact that when you look at it in one place, you say, "Oh, that's kind of a lot. Like I should cut that back." And then I have been successful in doing it that, and I don't. The hassle of a budget never made me stick to it.
Yeah, I'm exactly in the same boat, right? Like like there's a few things like, and think about it, right? Like cable and phone. Right away that's like, it could be up to $200 for some people, right? A month.
Yep.
That is absolutely gigantic. I mean, that dwarfs your gas bill. Well, maybe depending on
Your
how much you
coffee
drive. Well, that definitely dwarfs your coffee bill. But yeah, I mean, you're absolutely right that there's like a handful of things that people spend just an incredible amount of money on, and reducing even just a little bit there can make a huge difference. Like I was finally able to get my family off text messaging, and I mean that's significant. I mean, it saved us like $20 a month. I mean,
Wow.
it's like probably more than we spend in gas because I take the bus, I take the shuttle to work. So yeah, we probably saved almost our entire gas bill just in getting rid of SMS.
Nice. Yeah, and I like it for you looking at stuff, and like I said, the trends too. Like, wow, I spend how much on clothes or whatever. Like, oh, that's kind of crazy. And like,
Patrick, your clothes spending is out of control.
So like I know, like which is kind of obvious, I guess.
This.
But like November and December, we end up buying Christmas gifts or whatever for family, and so then like spending in November and December are typically high.
Right.
And so like, okay, like I know like to be careful the next couple of months and like stuff not related to Christmas spending that I can wait because I know Christmas spending is going to be high.
Yeah, don't buy that shirt.
Okay. Anyways, Mint.
Do you actually is clothes a large expense for you?
No, I was just trying to say something generic and not very personal.
I'm just giving you a hard time. That's my pet peeve. Is when I'm not giving Patrick.
Are you saying
a hard
I don't
time.
look stylish and handsome enough to be spending a lot on my clothes?
I think you look so handsome that I demanded you show your face in the podcast, in the stream. SimD.
All right, so right off the top.
Yeah, so SimD, right off the bat, we'll spoil it for everyone. Single instruction, multiple data. And so what that means is, like a canonical example is, I have 3 lists. I have 2 lists with a bunch of numbers in them, and then I have a third list that I want to hold the sum of the numbers of the first 2 lists. But I want to be like a element-wise sum. So like take the first element of the 2 lists, add them up. Take the second element of the 2 lists, add them up. And it's like the same exact instruction, right? So you could, you could as a, like if you could just have the assembly code or what have you say, put the first item in a register, put the first item from both lists in 2 registers, add them up, put that in the third list, do it again, do it again, do it again, do it again, right? But if you're doing something like so obvious, like the same exact operation, but you're just doing it on different spots of the memory, then you can do what's called single instruction multiple data, where you say something like, take these 10 things and add them together. But because you're doing exactly the same thing to all 10, you don't have to repeat yourself. You just say, do it to all 10. And it just kind of magically works. So
the way what this buys you is parallelism, as Jason described. So things go faster, and that's always a good thing. People like faster. And the way it works is in the processor, you can think about, so like as Jason was saying, you're, adding these element-wise, all these things in a list. So if you have each element in the list is 8 bits wide, and you have a 64-bit ALU, arithmetic logic unit, so you have the ability to add 64-bit numbers, you could add 2 64-bit numbers, or you could add 8 8-bit numbers. And the only difference is you need to prevent the carry between each 8-bit number. So typically there's a carry bit where, if 2 numbers are 1, in binary, it has to carry to the next digit. And so you need to be able to turn that off on the boundaries. So you have 8 with carries. Then you have a boundary between 8 bits that has the ability to either carry or not, depending on if it's a normal 64-bit add or a SIMD 64-bit add. And when you're doing a SIMD 64-bit add, on each of the 8 boundaries, or 7 boundaries, each of the 7 boundaries, you disable the carry bits. And so what happens
Gotcha.
is then when you add two 64-bit numbers, you're actually adding eight 8-bit numbers and storing the result with no carries between them. And so that allows you to do, instead of saying, normally you would have to move an 8-bit number into the 64-bit register, move another 8-bit number into the 64-bit register, add the two, store them in a 64-bit register, and then write that out to memory. But all the rest of that 50, but it's so late at night, 56. Oh man, it's too late at night. 56 bits are all just going to be zero. So you're adding 0 plus 0 plus 0 plus 0, 56 times. And that's just a waste. Right. So that's how SIMD buys you an advantage. And
I always thought that, I mean, and so correct me if I'm wrong, and I'm probably wrong, but what is, I always thought that it was a separate processor than the ALU.
So
I thought it was like a
sometimes not. It is, these are all, this is like at a fundamental architectural, like they share these similarities. But sometimes just like floating point unit can be a separate thing or inline, like it just is a architectural decision.
Gotcha. Okay, that makes sense.
And so what it turns out is normally the instruction set will support like 64-bit integers, but they'll have 128-bit two special 128-bit registers and corresponding ALU with this option. But they'll have the ability to do it on 32-bit boundaries, 64-bit boundaries, various divisions, because you may not always, you want to do as many as possible, but typically like the 8-bit boundary example I gave wouldn't be very useful. People don't want to only add 8 bits at a time. So you'd have like a 32-bit boundary, a 64-bit boundary, 128-bit boundary for 256-bit wide SIMD would be very common.
Gotcha. So if it's 256-bit wide SIMD, then you can do 8? 8. You can add 8 numbers in one instruction. Okay, got it.
Yep. But so typically, I think most of it, so we'll get to this in a minute, a lot of this is used for graphics. And so you're typically dealing with 32-bit numbers, and you want to do, we'll get to why later, 4 32-bit numbers. And so it's very common to have 128-bit.
Oh, okay.
But like I said, these are all just like, it's a concept, right? So I'm sure every variation has been done at some point. And that's kind of architecturally how it works. And like I said, the ALU is for addition, but it would also be the same supported operations for division, multiplication, reciprocals, bit masking, all those kinds of things would typically be supported in a similar fashion.
Gotcha.
We've previously talked a little bit about GPU programming. I think we did an episode on CUDA. And a difference between this and the way GPUs work is that in SIMD, if you have a branching logic statement, if statements, even though the GPU doesn't handle that great, it has support for handling it because each thing is running on its own minimally functional processor, but it is its own processor. So they can be doing slightly different things. You just lose some efficiency. But with SIMD instructions, you actually cannot. So you, like we said, you're treating, it becomes a 128-bit number, a 256-bit number, and it just has these weird boundaries within it. But you're responsible for shuffling the data into that number and back out. And so you can't make decisions like if the second item is this, and at the same time if the third item is this, like you would have to do those sequentially.
Gotcha. That makes sense.
And so that's a big difference. But the other difference is it's cheaper from a silicon perspective to implement this, right? So as opposed to a whole swarm of specialized GPU processors. Some of the common ones.
What about like performance? Like, is it the same? I mean, is it worse than a GPU or
different?
Oh, it's different.
Depends on what you want to do, right? Like, they're all different. So the GPU has advantages, but it's more costly, right? So you're not gonna typically. It's done in a different way. So like in a low power small processor, there's no way you'll ever have like a whole bunch of GPU cores.
Gotcha. Because they were talking at one time about like Intel wanted to put a GPU on the motherboard. Yeah.
No, on
the actual core. Yeah.
Yeah. So on die, but you still have to. Typically, you would still want different memory because the access patterns are different. And so you'd want to move back and forth between. Anyways, it gets complicated.
Oh, I see.
They're just two different tools.
Gotcha. Okay.
And so the things you may have heard of before, which are implementations of SIMD, specifically Pentium, if you remember way back, you would have heard of MMX processors. I think this is multimedia extensions. And so
Okay.
you'll often hear of these as like some sort of extension, because what it's saying is you have the normal instruction set, then there's some supported extension to that instruction set which allows for this, extra wide operations to take place. Also SSE. So SSE was simultaneous SIMD execution or extension, one of those.
Okay.
Something like that. So those are Pentium 1. So SSE, SSE2. So I think there's like
Yeah, there's
Pentium
a
3,
bunch of
Pentium
them,
4s.
right?
Yeah. So you'll have heard of those before. And then for ARM processors are getting powerful now, or getting common now. And ARM processors also have their version of SIMD, which is called Neon. And you'll hear these a lot with multimedia. And the reason why is because, like I was saying, so graphics processing, video codecs, audio, this kind of thing, because these have a lot of, I don't know the exact right word, blind operations, where you just want to blindly apply the same mathematical function to a lot of data all at the same time.
Okay.
And so these extensions are really good at speeding those things up. And you can get, like we were saying, so if you can do 4 or 8 32-bit instructions at one time, that's like a 4x or 8x speed up for that portion of the code.
Gotcha.
So some examples that we want to do, we talked about, like you could add two numbers in a list, you could do cross products, you could do dot products, you could do averaging. So averaging would be a little bit where you start to get into some trickiness, right? So for averaging, if you have, let's say, 4 32-bit numbers you can do at a time, and you have 16 items in your list, you'd want to add 2 sets of 4 twice. So you'd have 4 and 4, 4 and 4,
like,
and you do them
like
simultaneously, and then you'd have 2 sets of 4 resultant. Then you'd add those 2 sets. So now you've done 3 operations. This is really hard to describe over only audio.
It becomes like it's like a pyramid.
It's a pyramid, exactly right. So now you have done 3 operations. Then you will no longer be able to use SIMD really, because you need to add that one last remaining set of 4 together, and then divide by the total number of elements. But you can see how depending on how many operations you have, you can get a very large speed up.
Yeah, right. So just a shout out to PanoDK, who just subscribed to or followed the stream. So thanks.
Nice. Oh, he also had a suggestion about earlier.
We have our first follower, which is pretty awesome.
So another one you'll hear a lot is a 4x4 matrix multiply. And so in graphics, this is because you have typically 3-dimensional rotation matrices and coordinates that are stored for triangles and various, and you store the 4th one to account for some mathematical quirk. I don't know if we ever talked about that before.
Yeah, like the quaternions, right?
Yeah. So you typically do a 4x4 matrix
I feel like we
multiply.
talked about it briefly, but like, we didn't go into a lot of detail. But let's just say that there's some funky math you can do using 4D math, which has no relationship to what you're actually doing, but just mathematically like gives you some niceties. Is that like a one-liner that can kind of wrap it up?
And so I'm pretty sure this is 4x4 matrix multiply with pretty much all these kind of SIMD instructions that works really well, and gives you a big speed up because you're doing that over and over and over again, because you're doing coordinate transform after coordinate transform after coordinate transform.
Yeah. Just to put this in perspective, right? Like if you're doing, let's say you're making a video game, right? And you have some dude, like Grand Theft Auto style, and he's running and he's holding like 2 Uzis, like John Woo, like dual wielding Uzis, right? So now it's like you want to render, a bullet coming out of the Uzi. So you need to do a transformation to go from the universe to the camera, a transformation to go from the camera to the person you're looking at. That's another, matrix multiply. Then a transformation to go from that person's frame of reference to his hand, one to go from the hand to the barrel of the gun, and another one to account from the barrel of the gun out to the bullet.
Yeah,
right?
and even like if the bullet's rotating, like the spin of the bullet.
Yeah, then you have to do another one for that, for the spin of the bullet. Right, so you have to do like 10 of these 4x4 matrix multiplies just to like know where the bullet is. Like you haven't even drawn the bullet. If you want to draw all the little triangles of the bullet, now you have to do one of those for each of those triangles, right? So you're doing a lot of them.
So any speed up, and this is why, like I was saying before, these typically have names like associated with multimedia or graphics, is because that's where you'll see a lot of the use. Same thing like audio processing, you'll want to apply some filter, and typically at every point in the signal, you want to look at the surrounding few points. So now what you basically end up with is like you shift an element in, you apply the same operations. You shift the next element in, you apply the same operations. You just keep doing that over and over again. And this is where you can really get the kind of naive big speed ups because it's really, really well suited.
Gotcha. Makes sense.
But this takes a lot of like, hand power. And I've written in several of these SIMD languages. They're not called languages, SIMD styles. And it almost
extensions or
extensions, sure. And what it amounts to is you're writing assembly code. Like, you're not, but you are. Because you basically need to worry about everything. Like, I need to load up the special registers with data exactly arranged how I need it. Then I need to do specifically like these low-level operations. Then I need to get the data back out. These are the kinds of things you typically worry about when you're doing like assembly programming. And this is very, very similar. I find it. And so you typically kind of wrap it in a function. You stick that function somewhere and you call in with very nice data classes or objects, pass them in. Then you do this very kind of horrendous, but fast, assembly level kind of programming. And then you kind of pass it back out in a nice class.
Oh, gotcha.
That's the way I've kind of
what happens if you get it wrong? Like, I mean, it probably doesn't throw an exception, right? I mean, like, do you end up with weird numbers or does it like literally?
Well, it depends on what you mean by mess it up.
Well, let's say like you have some kind of out of bounds or something like that. Like, do you get weird numbers or does the whole
typically
computer
like wraps
crash?
or overflows or underflows or?
Oh, I see.
Yeah, it depends. But yes, this is the general flow of it. And so obviously that's painful. But the good news is if you're writing a graphics library and you optimize some part of that, right, people are calling into your API, not to your... They're not going to try to write these SIMD instructions themselves.
Yeah, that's true. I mean, for most people out there, you're just relying on, if you're using Unity or whatever for the game engine, you're relying on them to do this stuff for you. So, but actually, you can write code which does SIMD and not even know it.
What?
And that's with I know. That's automatic vectorization, which I actually remember when this came out. Like, I remember when GCC 4.7 came out, and it was like I just remember just my mind being blown because I don't really stay up to date on compilers, research or anything like that. So like I didn't realize that this was an effort, and then all of a sudden it's like, oh yeah, SIMD for free. It's just like, what? But yeah, basically, the compiler, the guys who write the compiler are very bright. They analyze your for loops, and if the for loop looks like it's doing something trivial enough that they can capture all of the side effects and isolate it, then they will try to replace your code with SIMD code, which does the same thing but much faster. It's pretty freaking amazing. In GCC 4.7, it was very, very simple. So even like you couldn't use a vector. If you had a vector of floats, the way that like vector, when you actually do the bracket on an STL vector, it passes it through this inline function. And most of the time it does nothing, but if you're in debug mode, it'll like check or do a couple other things. And just the fact that that function was in the way caused like all STL vectors to not be supported. And you actually had to like create a pointer of the vector and just like, so you basically have to do it yourself. But since then it's come a long way. And now even if like, you add 2 vectors of floats in C++, it'll vectorize it. If it can make some guarantees about the size and things like that, which is pretty cool. It's also coming to Java. It's not there yet, but that's one of these kind of amazing things. Like if they build automatic vectorization into the Java virtual machine, then like it's just going to completely change the runtime profile of every Java program ever. I mean, like who knows what's going to happen, right?
Yeah, I guess it depends on how they support it. I don't know the exact specifics, but yeah. The other thing, like we were saying, is like if your library like Unity or whatever supports it, you get it. Also, there are, of course, libraries, and I didn't write any down here because I'm not up to date on these right now, but where you could get a package of like, here's common operations you'd want to do. and here they are implemented in ways that are very amenable to GCC doing auto vectorization, or already have
cool.
SIMD instructions themselves, right? So you may
Right.
have like a wrapper that you pass in STL, like for instance, like Jason was saying, the STL vectors in C++ didn't work well. But you could have someone else, well, probably, and you can find it because I've seen these before, have written code that says like, here's how to do 4x4 matrix multiply in SIMD that takes in the vector, the STL vector, and outputs STL vector, right? And then
exactly.
It wouldn't be vector, it'd be the matrix, but takes in a matrix and outputs a matrix, and then it handles the exact massaging into the right form and back out, and that's the only thing it gets you right. And those are obviously very useful because it saves you a lot of time.
Yeah, one thing that I realized, I just searched on our programming throwdown sort of agendas of all time. We've never talked about BLAS. Do you want to talk about BLAS?
I think we should save it for a tool of the show.
Okay. All right.
Why don't you give the high level summary and then we'll save it.
So I don't know too much about it.
Oh, okay.
But
this is why you're telling me to do it.
So BLAS stands for Basic Linear Algebra System, and the idea is, if you want to like add two matrices or invert a matrix or do kind of these kind of mathematical operations that you do in like MATLAB or one of these other tools, but you're not using MATLAB, you're using Python or C++ or something. There's this set of libraries that are BLAS libraries, and basically it's what Patrick is saying. These guys have just killed themselves making like the most epic matrix inversion code ever, the most epic add two vectors together code ever, and you can just use the BLAS library whenever you want to do one of those things.
Yep.
So,
and they do some pretty clever stuff. Yeah. And there's some pretty clever stuff about how to determine, like, because there's no one right optimal way to do something. It's going to vary by your L1 and L2 cache size, by your number of hyper-threaded cores, and by the number of your processor clock speed, and like every variable of your computer system. And so
I made the mistake one time of compiling Atlas, which is a BLAS implementation. I didn't want to use the one that was like built into Ubuntu, and I was like, I'll just build my own. And it took something like 8 hours to build. And basically it's like, trying every
permutation.
It's like trying every possible way to build this library just to give you an extra 1%.
I've never looked. Because, I don't know. Well, we can talk about it later. I don't know if they do something intelligent like gradient descent or something, or if they just straight out like try every permutation.
Yeah, I don't know if they do like something intelligent, or if it's just like you said, it's just a raw parameter sweep.
Okay.
But yeah, it takes a really, really, really long time, and most OSs will have it built in,
and it'll be 90-something%. I'm making up a percentage, as fast as it can be. But if you compile it yourself, they do some really clever things to make it as fast as can be.
Yeah, that's right. Like the one you get from Ubuntu isn't made for your machine. It's made for, someone's machine who's building the Ubuntu distribution. And so, Patrick's right. Like if you build it from scratch, after the 8 hours, you will have something that is like 1% faster.
But that
or more, maybe.
Yep.
Yeah.
So everything's on the web now, and everybody's trying to do graphics on the web. So of course, SIMD is coming to the web.
Yeah, that's pretty wild, right? I mean,
so if you're going to do gaming, like I said, this is all about like doing graphics processing, audio processing, video processing, all things that have a very legitimate reason these days to be done in a web browser. And if you're going to do that, you're going to want to take advantage of SIMD because it does give it's very conceivable to have like an 8x, 10x improvement by implementing this stuff. And that's big. Yeah,
totally. I mean, me and some buddies wrote an emulator in effectively JavaScript. We wrote in Dart. Actually, we talked about it on one of our shows. And the emulator, like rendering all the pixels actually only takes like 1 or 2% of the time. But just executing the Nintendo CPU, which is just, like a 1 megahertz CPU or something ridiculous, takes like over 90% of the time. And it's because a lot of the times you're doing simple operations, but on the web they're just so painfully slow. And And so this SIMD is part of a bigger effort to sort of fix that problem.
Yep. So this is SIMD is going to be added to Dart, or so it said a year ago. So I assume it's already there.
Oh man, you're right. This is a year old. I didn't even notice.
So you're starting to see a lot of these things, and again, you will continue as more and more people do stuff in the browser. So.
Yeah, totally. I mean, I think that it's only a matter of time before we get, like, we already have Nscripten and some of these technologies for taking, like desktop applications and basically compiling them for the web, and it just kind of magically works. But it's still like very early stages. And so this is like sort of building more of that scaffolding so that we can one day get to a place where you could just build something for your desktop and the web, and it would just kind of magically do what you want.
Well, I think that's a wrap.
Yeah, cool. Thanks everyone for following us on the stream, and we got some good feedback there. Pretty cool. It's been a while since we did a show, but as you can expect with the vacation, I was on vacation, Patrick's on vacation, Thanksgiving's coming up, so it's that time of year where it's hard to find time.
We'll try to do one before Christmas, but it may end up being January.
Yeah, it's possible, but we should be able to.
We've got time
to grab some time. I think we can pull it off. But if not, we'll see you guys in January. But but anyways, it's always fun to do the show, and I'm trying to think. Do we have anything news-worthy, like meta? Anything
meta
to talk about?
Like how many reviews we have or anything. So
yeah, I don't think we have much meta to say. This is a pretty cool one. I definitely want to cover Rust, that programming language, and we got some other requests for languages, so we'll be covering that. We get a lot of, actually the majority of our feedback is still on Google+, which is awesome. I mean, we have the Facebook and the Twitter. A couple of people asked for those, but still, the majority of the content is happening on the G+ page, so definitely check that out. And send us email. We read all of them. Sometimes we read them on the show. Sometimes we say your full name and embarrass you. I
don't think we've ever read anybody's name who told us not to, but
no, I'm totally kidding. Yes, I mean if you want to
remain anonymous, we will do that.
Yeah, if you want to remain anonymous with your anonymity,
keep your anonymity intact. All right, it's late,
so
we're gonna call it a wrap.
All right, see you guys later.
Stopping recording.
The intro music is Axo by Binar Pilot. Programming Throwdown is distributed under a Creative Commons Attribution Share-alike 2.0 license. You're free to share, copy, distribute, transmit the work, to remix, adapt the work, but you must provide attribution to Patrick and I, and share alike in kind.